Welcome back, everyone, for another deep dive. And this time, we're going to be talking about something pretty interesting in healthcare,
Yeah,
which is how AI can actually handle all the uncertainty we have in medical data,
right.
like especially when you're trying to predict those like rare conditions that don't happen very often.
Yeah,
It's like finding a needle in a haystack, right?
yeah, absolutely.
You actually shared some research on a really interesting approach.
Yeah.
It's called RIGA,
The written.
Robustness, using Imbalance-Resilient Generative Augmentation.
Yeah.
That's a mouthful.
Yeah, it is.
So can you kind of give us like a quick overview of what this RIGA thing is all about?
So RIGA is basically a new way to solve the problem of imbalanced data sets
Okay.
that we see in healthcare a lot. So
Yeah.
think of like predicting preterm birth.
Right.
Thankfully, this doesn't happen very often.
Yeah.
So this means there are very few examples for our AI models to learn from,
Okay.
which in turn makes it very difficult to actually make accurate predictions.
Ah,
So what RIGA does is it creates synthetic data to kind of balance that out.
I see.
So it basically generates more examples of those rarer cases to help the AI learn.
Okay, so it's like giving the AI like a bigger training set, even if in the real world that data is actually really limited.
Exactly.
That makes a lot of sense.
Yeah.
But here's where things get interesting for me, at least.
Yeah.
RIGA actually involves turning that data into images. Now, we're not talking about like X-rays or scans here, right? This
Yeah.
is like stuff like patient records, blood test results, that kind of thing.
Right.
How do you even turn that into like a picture?
It might seem counterintuitive at first,
Yeah.
but it's actually surprisingly effective.
Okay.
So in the first phase of RIGI, we call it data transformation.
Okay.
And this is where a method called deep insight comes in.
Deep insight.
Yeah. So deep insight essentially analyzes the relationships between different features in your data.
Okay.
So for example, it might identify correlation between blood pressure and heart rate.
So deep insight is kind of like figuring out which data points tend to go together like pieces of a puzzle.
Exactly.
I'm starting to see the picture here, literally.
Yeah, precisely.
Haha.
And so based on these similarities, deep insight will actually arrange the features in a 2D space,
Okay.
kind of like plotting points on a graph. But instead of a scatter plot, we get an image
I see.
where each pixel will represent a specific feature.
Okay.
And the intensity of each pixel corresponds to the value of that feature
For a particular patient.
for a particular patient, exactly.
So instead of rows and columns in a spreadsheet,
Yeah.
we now have this visual representation of the data. That's
Mm.
really clever.
Yeah, it is.
But is anything lost in this like transformation?
That's a great question.
Yeah, like could we go back to the original data if we needed to?
Yeah, absolutely. This transformation is what we call lossless.
Okay,
So no information is lost.
that's good.
And we can actually convert the image back to the original tabular format if needed.
Hey, that's reassuring. No data left behind in the art studio?
Exactly.
But why even go through all this trouble of creating images in the first place?
Right.
What's the advantage here?
So that actually brings us to the heart of RIGA.
Okay.
It's phase 2, which is augmentation. And this is where the power of generative AI comes into play.
Generative AI.
Yeah, so remember those imbalanced data sets we talked about?
Yes.
Well, RIGA uses these data images
Right.
to create synthetic data
Yeah.
specifically for the underrepresented class.
Okay.
It's essentially filling in those missing pieces of the puzzle.
So if we're trying to predict like preterm birth, for example.
Yeah.
And there's not that many real world examples.
Right.
RIGA can actually generate more examples of what that would look like in the data.
Exactly.
And this gives the AI more to learn from.
Yes, exactly.
Okay.
So the researchers actually used 3 different generative models in their study.
Okay.
One is called a conditional GAN, or cGAN for short. And it's great because it can create images based on specific conditions.
Okay.
So in our case, this would be trained on images representing like full-term births.
Okay.
And then it can be used to generate examples of what preterm birth might look like based on the patterns it's learned.
So it's like giving the AI the ability to imagine scenarios based on real world data.
Based on real-world data, that's a great way to put it.
That's pretty cool.
Yeah.
But I'm guessing cGAN isn't the only tool in the box here.
You're absolutely right.
Yeah.
They also explored using something called VQVAE, which stands for Vector Quantized Variational Autoencoder.
Wow, that's a mouthful.
Yeah, it is a mouthful.
Can you break that down for us a little bit?
Yeah, so imagine you're trying to solve a puzzle, but you only have a handful of pieces.
Right.
It's going to be pretty difficult,
Yeah,
right?
yeah.
So VQVAE is like finding a blueprint that captures the essence of all those missing pieces.
Okay.
And it learns a compressed representation of the data and then uses that to generate new samples.
So it's not just copying existing images.
I don't know.
It's learning the underlying structure of the data
Yeah.
and using that knowledge to create these new variations.
Exactly.
Okay.
And then they took things even further by combining the power of VQVAE with GANs
Okay.
to create what's called a hybrid model.
Okay.
And we call this VQGAN.
VQGAN.
Yes.
I'm sensing a theme here.
Yeah.
A lot of acronyms, but
Lots of acronyms.
they all revolve around generating new data in some way.
Yeah, that's the main goal.
Okay, so what exactly does VQGNN bring to the table that's different from the other two?
So think of it this way. cGAN is like a really talented artist
Okay.
who can create realistic images based on your instructions.
I like it.
While VQBAE is like this master puzzle solver,
Yeah.
that's really good at understanding the underlying structure of the data.
Right.
So VQGAN basically combines the best of both worlds,
Okay.
allowing for even more realistic and diverse synthetic data generation.
So it's like the ultimate data image factory,
Sure.
churning out all these synthetic examples to help balance the scales.
Yeah.
But once we have all these images, real and synthetic, what do we actually do with them? How does this actually help us like predict things like preterm birth?
So that brings us to phase 3,
Okay.
which is classification.
Okay.
And here's where RIGA offers some flexibility.
Okay.
You can actually classify the data in 2 ways.
In 2 ways.
Yeah. The first way is by using a convolutional neural network, or CNN,
CNN.
directly on the images.
Okay.
So CNNs are a type of deep learning model that's really good at image recognition.
So we're basically asking the CNN, hey, based on these visual patterns, does this look like a preterm birth?
Right.
We're treating medical data like cat pictures on the internet.
Exactly.
Uh-huh.
But RIGA also allows you to go back to the tabular world.
Okay.
You can transform those synthetic images back into their original format,
Okay.
with the rows and columns using the inner deep insight process.
Right.
And then you can apply more traditional machine learning algorithms like XGBoost.
So RIGA gives you options, which is always a good thing, I guess.
Exactly. It's all about having choices.
But I'm curious, why would you want to go back to the tabular data
Yeah.
after all the effort of turning it into images in the first place?
Well, sometimes certain machine learning models are actually better suited for tabular data.
Okay.
It really depends on the specific task and the nature of the data.
Yeah.
It's kind of like having different tools in your toolbox.
Right.
You choose the right tool for the job.
Makes sense.
Right.
So how do we actually know if this whole image-based approach is working?
Right.
What metric did the researchers use to measure success?
So they focused on a metric called AUC,
AUC.
which stands for area under the curve.
Okay.
And it's a measure of how well the model can distinguish between different classes.
Okay.
In this case, preterm birth versus full-term birth.
So a higher AUC means the model is doing a better job at correctly identifying those rare cases.
Exactly.
Which is really important in healthcare,
Absolutely.
where accuracy can have a huge impact on patient care.
Absolutely, it's crucial.
Yeah.
But RIGA isn't just about making better predictions.
Okay.
It's also about deepening our understanding of the data.
I see.
And that's where the 4th phase comes in.
Okay.
Bayesian network learning.
Okay, we haven't talked about that yet.
Right.
What are Bayesian networks?
Yeah.
And how do they fit into all of this?
So think of a Bayesian network as a map of relationships between different variables in the data.
Okay.
It helps us understand not only what might happen,
Okay.
but also why.
So in the case of preterm birth,
Yeah,
it's not just about predicting if it will happen, but also understanding which factors might be contributing to that outcome.
exactly.
Like genetics, lifestyle, environmental factors, all of that.
All of those things, yeah.
Okay.
And the research has actually found that by using RIGA's augmented data,
Okay.
they could build better Bayesian networks,
Interesting.
revealing more complex relationships that weren't really clear before.
Okay.
And they actually used a metric called BIC,
BIC.
which is Bayesian Information Criterion,
Okay.
to assess the quality of these networks. And RIGA consistently led to improvements in that score.
That's pretty remarkable.
Yeah, it's really cool.
So RIGA is kind of like a 2-for-1 deal. Again, better predictions and a deeper understanding of the data.
Exactly.
But enough with the theory. Let's get to the results.
Right.
How did RIGA actually perform when tested on real data sets?
Yeah.
Did it live up to the hype?
So the researchers tested RIGA on 4 different data sets.
Okay.
Let's start with NOMO-M2B,
Numo M2B.
which focuses on predicting preterm birth.
Right.
They found that using RIGA with VQGAN augmentation
Okay.
significantly improved the performance of both the CNN and XGBoost models.
So the model that combined the power of the autoencoder and the GAN
Yes.
was the most effective.
Yes, it was.
Interesting. Any insights into why VQGAN performed so well with this data set?
It likely comes down to the complexity of the data itself.
Okay.
So NOMO-M2B includes hundreds of features, all these different variables that could potentially contribute to preterm birth.
Right.
And VQGAN, with its ability to capture these really intricate relationships, was able to generate very realistic and diverse synthetic examples that really closely resembled the real data.
It's like VQGAN was able to grasp the nuanced interplay of factors that influence preterm birth, allowing it to create synthetic examples that truly reflect the complexity of the real world.
Exactly.
That's pretty cool.
Yeah.
Now let's move on to the Madelon data set,
Okay.
which is synthetic.
Yeah.
So this was like a way to test how well RIGA performs even when the data is intentionally designed to be tricky.
Exactly. Think of it as a deliberately challenging obstacle course for the AI.
An obstacle course, I like it.
And again, VQGAN was the clear winner,
Okay.
improving both CNN and XGBoost performance significantly.
It seems like VQGAN is on a roll.
It was doing really well.
Yeah.
Yeah.
But what about the other data sets?
Yeah.
The Myocardial Infarction and DARWIN data sets?
Yes.
Did VQGAN continue its winning streak?
So that's where things get even more interesting
Oh.
for the Myocardial Infarction data set,
Okay.
which deals with complications after a heart attack.
Right.
RIGA actually faced some challenges.
Really?
Yeah.
What happened there? Was the data too complex even for VQGAN?
It's possible this data set had fewer features
Yeah.
and a much smaller number of examples for the rare class,
Right.
which made it more difficult for the models to learn,
Okay.
even with the synthetic data.
So even with the augmentation, there just wasn't enough information
Yeah.
for the models to truly get a handle on the patterns.
That's likely a contributing factor, yeah.
Okay.
Additionally, the generated images for this data set
Right.
might not have captured the nuances as effectively,
Okay.
which then led to less accurate predictions.
So it highlights that the choice of the generative model and its tuning
Yeah.
really need to be tailored to the specific characteristics of the data.
Exactly.
So it's not a one-size-fits-all solution. The success of RIGA seems to depend on the nature of the data itself.
Absolutely.
Okay, what about DARWIN?
Yeah.
How did it fare in predicting Alzheimer's disease?
So with Darwin, we saw a shift. VQVAE,
Okay.
the autoencoder without the GAN component,
Right.
actually performed the best.
Wow, so VQGAN was dethroned.
It was dethroned.
What made VQVAE a better fit for this particular data set?
So the Darwin dataset is relatively small.
Okay.
And sometimes with smaller datasets,
Yeah.
complex models like VQGAN can actually run into problems.
Okay.
They can start to overfit,
Overfit.
which means they learn the training data too well,
Okay.
and then they don't generalize well to new data.
I see. It's like trying to learn a language from a single short story.
Uh-huh.
You might memorize it perfectly,
Yes.
but you won't be able to have a conversation.
Exactly.
So in this case, VQVAE, with its simpler structure,
Right.
was better suited for the task.
Exactly. It was able to capture the essential patterns without getting bogged down in the finer details.
Yep.
And this just reinforces the idea that there's no single best model for every situation.
Right.
The choice really depends on the specific data and the problem you're trying to solve.
That's a great point.
Yeah.
But before we move on, you mentioned that RIGA can also help us understand the data better through Bayesian networks.
Yes.
Can you give us a specific example of how that played out with one of these data sets?
Absolutely. Let's look at the NUMO M2B dataset again.
Okay.
After applying RIGA, the researchers found that the Markov blanket for the outcome, preterm birth, expanded.
Now, I'm not familiar with that term. What's a Markov blanket?
So it's basically a set of variables that are directly related to the outcome you're interested in.
Okay.
Think of it as identifying the key players in the network of factors that influence preterm birth.
Okay, I'm with you. So how did RIGA change the Markov blanket in this case?
So after using RIGA, the Markov blanket actually included more variables, which means they were able to uncover more complex relationships within the data. For example, they found a stronger connection between smoking habits during pregnancy and preterm birth.
Interesting.
A relationship that wasn't as evident before.
So it's not just about making the model better at predicting preterm birth.
Right.
It's about shedding light on the underlying causes.
Exactly.
And potentially paving the way for more targeted interventions.
Yep.
That's incredibly powerful.
It really is.
Yeah.
And it highlights the potential of RIGA to not only improve predictions in healthcare, but also to really advance our understanding of these really complex medical conditions.
That's huge.
Yeah. But of course, no approach is without its limitations.
Right. What are some of the potential drawbacks or challenges with RIGA?
Well, as we saw with the Myocardial Infarction dataset,
Yeah.
RIGA isn't a guaranteed win every time.
Right.
The choice of the generative model and its specific parameters really need careful consideration based on the unique characteristics of each dataset.
So it's not like a plug-and-play solution.
Right.
It requires some expertise and fine-tuning.
Yeah, to get the best results.
Absolutely.
And there's always a risk that the generative models might create synthetic data that doesn't accurately reflect the real world.
That's right.
And this could lead to biased or misleading results.
Exactly. It's a possibility.
That's a really important point.
Yeah.
So careful evaluation of the synthetic data is crucial to ensure that it's truly representative and doesn't introduce unintended biases.
Absolutely. You have to be very careful.
Yeah. It sounds like Rick has the potential to be like a real game changer in healthcare AI.
Yeah.
But it's still early days. So what are some of the future directions for this research?
Right.
What are the researchers working on now?
So one exciting avenue they're exploring is incorporating an error feedback loop into the system.
An error feedback loop. That sounds interesting.
Yeah.
How would that work?
Essentially, it would allow the generative models to learn from their mistakes.
Okay.
So if the synthetic data leads to inaccurate predictions,
the system can adjust and try to generate more realistic examples.
So it's like giving the AI a tutor who provides feedback and helps it improve over time.
Exactly. It's a continuous learning process.
That's a really cool idea.
Yeah.
It's like the AI is constantly refining its understanding and getting better at generating those synthetic examples.
Yeah, exactly.
Are there any other interesting directions they're looking at?
Yeah, they're also interested in using RIGA to further enhance Bayesian network learning.
Okay.
They believe that with even more refined synthetic data, they can uncover hidden correlations and gain an even deeper understanding of these complex medical phenomena.
That's really exciting.
Yeah.
It sounds like RIGA has opened up a whole new world of possibilities for healthcare AI.
It really has.
So as we kind of wrap up this deep dive,
Yeah.
what are some of the key takeaways you want our listener to ponder as they go about their day?
Well, first, I think it's incredible how RIGA is pushing the boundaries of what's possible in healthcare.
Right.
I mean, turning data into images might seem a little strange at first.
Yeah.
But it's unlocking all these new avenues for analysis and augmentation.
It's like we've given AI a new lens to view medical data through, allowing it to see patterns and connections that were previously hidden.
Exactly. And the fact that this approach can improve the accuracy of predictions
and
enhance our understanding of those really complex medical relationships is truly remarkable.
It's a good reminder that AI isn't about replacing human intelligence. It's about augmenting it, helping us to see things more clearly and make better decisions.
Absolutely.
And I think the results with the different data sets really underscore an important point. There's no one-size-fits-all approach in AI.
Right.
Choosing the right tools and techniques is crucial.
It is.
And it depends entirely on the data itself and the specific problem you're trying to solve. solve. It's all about being a thoughtful and informed user of AI.
Yeah.
Understanding its strengths and limitations.
Absolutely.
Like, with any powerful tool, we need to use it responsibly.
All right.
And with careful consideration.
I agree.
And finally, I believe this research shows just how much potential AI has to transform healthcare.
It's huge.
We're just starting to explore what's possible.
Yeah, we are.
And it's an exciting time to be involved in this field.
It really is.
So to our listener out there,
yeah,
keep asking those curious questions.
Right.
Keep exploring those cutting-edge ideas.
Keep learning.
The future of healthcare is being shaped right now.
It is.
And it's a future full of amazing possibilities.
Absolutely.
Maybe this deep dive will even inspire you
to
come up with the next breakthrough in healthcare AI.
Who knows?
Thanks for joining us on this journey, and until next time, stay curious.
Thanks for having me.